Welcome back to the third lecture in the mechanics section of the IB Physics syllabus. Today, we're looking at work, power, and energy. I have to say this is one of the easier topics in the IB Physics syllabus, so if you get really good at this, it's free marks on the exam compared to some of the harder topics that are more contextual. So let's get right into it. The main thing about this topic is that energy is always conserved. There's something called the principle of conservation of energy, and that basically states that energy cannot be created or destroyed. It can only be transferred from one form to another. That pretty much means you cannot make energy and you cannot break energy. All energy that has existed right now has existed since the start of the universe, and it just keeps transforming from one form to another. So, for instance, from sound to heat, and from heat to maybe rotational energy, and from rotational to electrical energy, perhaps. Something like that. So, it's very cyclical. And basically, the takeaway from this is that total energy always remains constant within a closed system. Now, a closed system basically is something where energy cannot move in or move out. We'll look a lot deeper at systems in thermodynamics, but as of now, this is all you need to know. So let's take a look at this diagram here first. So this diagram shows how this roller coaster at the top has only potential energy up here. So that means because of its height, it has only potential energy. Then it falls, so now it has both potential and kinetic energy because it's now moving. And at the bottom here, it doesn't have any potential energy, only kinetic energy from the frame of reference of the roller coaster. And then up here, it again has potential and kinetic energy. Now, if you didn't understand what those words are, you don't need to worry. We'll cover them very briefly and then we'll come back to this. So these are the types of energy we'll be looking at. So mechanical energy, this is a type of energy which is made up of other types of energies. So you combine them together to get this. Thermal energy, so this is just means heat. So if you light a campfire, then you've transformed some chemical energy into thermal energy. Nuclear energy, so this is what you see in nuclear power plants. We'll look a lot deeper into this in the section E.4 and E.5 of the IB Physics syllabus, but for now you just need to know that it's energy created by a radioactive source. Then chemical energy. So chemical energy basically means the type of energy that's stored inside a battery. So energy created by chemical components. And then electromagnetic energy. This is not something that we'll really look at right now because it's a little bit more complicated. We can dig a little bit deeper into that during the D.3 and D.2, D.3, and D.4 sections of this topic of the syllabus. Sonic energy. This just means sound. Me speaking right now, that's sonic energy. Gravitational energy is basically the energy due to the weight of the object. Kinetic energy is just energy due to motion, and potential energy is just the energy that something could potentially get because of a property. So, for example, how far it's stretched or its height above the surface, something like that. And then ionization energy is sort of the energy with the ions. That's not something we really look at in IB physics. So let's take a look at dissipation of energy. So even though energy is always conserved, transitions between energy forms are never 100% efficient. Some energy is dissipated into the surroundings as heat energy. So if you think about it, if you leave a glass of hot water outside and you just leave it on a cold day, you just leave it outside, in a couple of minutes it's not going to be that hot. So it's lost its heat, its thermal energy to its surroundings. This is called wasted energy. Even though it's not even though the energy is conserved and being transformed into a different type of energy, it still can't be put to any use, right? It can't be used to heat up that water again. So that's why it's called wasted energy. And we represent this dissipation on this sort of arrow diagram called the Sankey diagram. The arrows point to the flow direction. So what we're looking at right here is a Sankey diagram for a light bulb. So the main purpose of a light bulb is to provide light energy. So as you can see, this straight arrow here is the main purpose. Now this big arrow here shows wasted energy, the energy that has been spilled out, and the line width shows the flow amount of energy that has been wasted. So in this case, only 10 out of 100 joules has been put to lighting on the light bulb. That means that only 10% of the energy has been used, and so the arrow here is only 10% of the width of this 100 joule arrow. However, here 90% of the energy has been lost to heat. That means that the width of the heat energy arrow that goes outside, showing that it's wasted, is 90%. So now let's take a quick look at work. Work done by a force is equivalent to the energy transferred. Work is basically the transfer of energy when an external force causes an object to move in a direction. So as you can see here, there's an external force of 100 newtons acting on this 15 kilogram object, which we can assume is causing it to move. That basically means that the object is doing work. And work is defined as the force times the displacement. So if we say this 100 newton force pushed this 15 kilogram object 5 meters, then we've done 100 times 5, so 500 joules of work. Work is measured in joules, just like energy, and we'll look into that a little bit deeper. So now if the force is actually at an angle to the displacement, so we're displacing the same 15 kilogram object to the right, but now instead of being directly perpendicular to this sort of wall of it, it's acting at like 60 degrees from the vertical, we can see that it's actually the cosine of that angle. So we take the angle to the horizontal here, and we just take the cosine of this angle to the horizontal to find the horizontal component of this force. So in this case it would be 100 cosine 30 is this force, and then the displacement would be 5, so we just have 5 times 100 times cosine 30, so we have 500 cosine 30 degrees. And you just type that into your calculator or use the unit circle. So now let's take a look at kinetic energy. This is probably the most important type of energy on the exam. And kinetic energy is just the energy that an object has because of its motion. So that just means the faster the object moves, the higher the kinetic energy. And an object maintains kinetic energy unless its speed or its mass changes. So here's the formula of kinetic energy. This is measured in joules as well, and it's basically a half times the mass times the velocity of the object squared. Now, as we can see from the formula, kinetic energy is directly proportional to the mass of the object. So if the mass increases, as in gets heavier, then it has more kinetic energy, and if it decreases, it has less kinetic energy, assuming that the velocity stays the same. It's also proportional to the velocity squared. So if the velocity increases and the mass stays the same, kinetic energy increases, and if the velocity decreases but the mass stays the same, then kinetic energy decreases. Now, you might notice something in this formula. This mv in the middle, if we ignore the squared sign here, is basically momentum. So we have a half times momentum times velocity, because we have velocity squared, right? So we factor out one of these v's. So we have a half times momentum times velocity. Now, how can we write this in a more accessible format? Well, kinetic energy depends on momentum as well. So if we write it as p squared by 2m, this is equivalent to saying kinetic energy is a half mv squared. So this is another form that you can write kinetic energy in terms of momentum. So now let's take a look at gravitational potential energy. This is another really important type of energy for the exam. This basically just means the energy stored in an object due to its position in a gravitational field. The object's gravitational potential energy depends on its mass and its height, as well as gravity, but for the most part in this mechanics unit we assume gravity as being 9.81 meters per second squared, so we can just say that it depends on the mass and the height. If the object falls, the gravitational potential energy decreases because this delta H here becomes negative. The final height is less than the initial height. So we have a smaller uh, gravitational potential energy. If it's raised, the gravitational potential energy increases. That basically means that the final height is higher than the initial height, so delta H is positive, so it's higher. So let's take a look at what happens to kinetic energy and gravitational potential energy. You can think of these as inverses. As one of them increases, the other falls. And that's always true because of the conservation of energy that we have. So this is within a system where the only two types of energy are potential energy and kinetic energy. While this sort of system is very unlikely to happen in real life because of wasted energy through things like thermal and sound, if we assume this ideal condition, then we can see that the total energy stays the same. As gravitational potential energy increases here, kinetic energy is decreasing. At one point, they equal each other so that the total energy is the same as 2 times potential energy or 2 times kinetic energy at this middle point here. And then, once kinetic energy reaches its lowest, the potential energy reaches its highest because of the conservation of energy. And as you can see, the highest is the same as the initial E. So let's take a look now at elastic potential energy. This is the energy stored in an elastic object, which is basically a spring, when the spring is compressed or extended. So as you can see here, the spring is the normal size. When we pull it apart, this distance here that we've pulled it apart is the delta x, so the extension. And when we push it together, this distance, so from here till here, is the negative extension that we've had it as. So we usually define pulling it apart as a positive extension and pushing it together as a negative extension. That's known as a compression, by the way. And we calculate this using half times k times delta x squared, where delta x, this difference in displacement between the two positions. K is the spring constant that's given to you in the question. We can also rewrite this using Hooke's law as half times f delta x squared, as Hooke's law says that the force is equal to negative k times x. We know that the magnitude of the force is k times x because the direction of the force doesn't really matter for energy. Energy is a scalar quantity, so that's why the negative is not important. So we can just rewrite this as a half times kx times delta x. And this gives us a half times force times delta x by Hooke's law. This second formula is not given in the data booklet, so it is suggested that you know how to derive it or you memorize it. Now let's take a look at mechanical energy. Mechanical energy means that we always have the sum of gravitational potential energy, kinetic energy, and elastic potential energy. And mechanical energy is always conserved. That means as one of these three things increases, the other two will have to decrease by the proportional amount in order to make sure that the total energy is maintained. So let's take a look at this system. In this system, the elastic potential energy can be assumed to be zero because there's no compressions or extensions. So at the bottom here, this has a kinetic energy which is very high and a very low potential energy because it's not high up. So the mg delta h is 0. So as we move up this thing, the potential energy increases and the kinetic energy decreases in order to keep mechanical energy constant. At the top here, it stopped moving momentarily. That means that the kinetic energy is 0 because velocity is 0, but as the height is so high, the gravitational potential energy is at its maximum, and that maximum is now equal to the mechanical energy. And now as it continues to fall again, kinetic energy starts increasing due to the acceleration due to gravity, and the gravitational potential energy begins decreasing because it's losing height. So that's basically the entire essence of this topic. Let's now take a look at power. Power is nothing to do with how strong you are, unfortunately. Power just means the rate at which you do work. And the rate at which you do work is also the rate of energy transfer. And so we can write power as delta work by delta time, where delta means change in. So delta work is change in work divided by change in time, and this is power. Now, if we again derive this using other formulas, we get that power is equal to force times velocity. But you can only use this formula when the object is traveling at a constant velocity v with a constant net force F. That's because it's been derived through Newton's second law, and Newton's second law assumes that acceleration is constant. So be very, very careful when using this formula here. The IB often likes to use trick questions with this formula for those who don't understand the context, usually with changing velocities or changing forces. So please do be careful. So now let's take a look at energy efficiency. This is probably one of the easiest parts of this topic, and it just means how well does the system use its input energy when creating output energy. So this little symbol here, that's the same symbol we use for viscosity, so just make sure not to confuse it with that, is energy out divided by energy in. That pretty much just means how much energy have I derived from putting this amount of energy in. It's just like a ratio of how effective my system is. Now, the energy out is equal to the energy by the energy in is equal to the power out by the power in, because power is just energy by time. And so the by times cancel each other out when you divide power by power. So we have the equivalent expression here. So you can use either one when you're looking at energy efficiency. So that's the end of this topic. I suggest you try this question and we'll work through it together. An engine is exerting a horizontal force F on an object that is moving along a horizontal surface at constant velocity v. The mass of the object is m, and the coefficient of dynamic friction between the object and the surface is mu. What is the power of the engine? Now that you've had a chance to try it, let's solve the question together. So the engine is exerting a horizontal force F on an object that is moving along a horizontal surface at a constant velocity v. The mass of the object is m, and the coefficient of dynamic friction between the object and the surface is mu. So what is the power of the engine? We're looking for power. Okay, so if this object here is moving at a horizontal force F like this, and we call this F, we call this F like this, ignore this please. Then if it's moving at a constant velocity, the friction backwards, which we can call small f, is equal and opposite to this big F. So that basically means if we find this friction, we can express this big F in terms of small f. So let's try that. So we know that friction is equal to mu. So that's the coefficient of friction times the normal force. And because this is horizontal, that means that normal force here is just this, which is an equal and opposite force by Newton's third law to the weight of this object. So that means that normal force is just the same as mg. Now, we know that this force here is constant because it's given that it's moving at a constant velocity. So now we know that power, which is what we're trying to find, is equal to force times velocity. And velocity is just v, and force is mu mg. So now we have mu times m times g times v. So our answer is answer option D. This is one of the trickiest questions in the entire paper 1 exam because it combines both 8.2 and 8.3 together. So it's something that you'll have to watch out for on the exam. I hope you found this video tutorial helpful. Please let me know if there's any other questions in the comments down below. Thank you.